This is October, November 2024, paper 22, A-levels 9702. This is our grade threshold out of 60. And let's try to solve this paper. So what is meant by vector quantity? It is quantity with a magnitude and direction, simple and straightforward. A sphere falls vertically through liquid, has a density this much. The sphere has a radius r, constant velocity. Now this is important, constant velocity v. The drag is given to us by the formula, this one. He says the n is property of the fluid. Find the base unit of n. So let's write down the base units of this equation. So d equals to 6 pi Rn v. Now the good thing about these questions will be he will mention what everything represents. So 6 and pi are actually constant. They will not participate in this. R was the radius, so this will be meters. Multiplied by n, we don't know. Multiplied by v is actually the velocity if you go back to the question. Velocity v. So we know this is going to be ms minus 1, and d, since d is a force, drag, we know that force is equal to ma, which can be kg ms minus 2. So equals to kg ms minus 2. This is our equation, and this is what we want to find out the base units of. So you can clearly see that one of the meters will be cancelled with this one. This ms minus 1 taken to the other side makes this unit of n equals to kg m minus 1 and s minus 2. So the base units will be kg m minus 1, s minus 2. It's algebra, nothing too difficult. State an equation showing the relationship between the magnitudes of weight, drag, and upthrust. So now, since he mentions that it's moving down, drag should be opposite of the movement. That is the pure understanding of this. And weight is, since it is moving down, weight will be downwards. Weight is always downward because of the Earth's gravity. Upthrust is always in the upwards direction, no matter if the ball is moving down or up. Drag changes its orientation. If the ball was moving up, then the drag would be downwards. So because drag purely opposes motion. In this one, he says that it falls vertically downwards, which means it's going down. Drag will be upwards. This is my upthrust. And if this is moving at a constant velocity, which means that the acceleration is 0 and the resultant forces on the object are 0, which means that all the upward forces, which will be upthrust plus the drag, are actually equal to the weight. They're all equal to each other. And that is what we're going to write down over here. So drag plus upthrust are actually equal to weight. You could have written down as W equals to upthrust plus drag. Both are correct orientations. He says the volume of the sphere is this much. It's in centimeter cube. Be careful. The drag force is 0.32. Calculate the weight of the sphere. So we're going to use this equation to find the weight. So which will be, let's rewrite the equation over here. W equals to upthrust plus the drag. You see, weight is what we need to find out. The upthrust is not given to us, but the drag is given to us. So let's find out the upthrust first, which is by a simple formula, Archimedes principle, rho g v. And v is the volume of the displaced liquid you're talking about. The density of the liquid itself was given to you in the previous part, which was 830. And this one would be 830 multiplied by g, which is 9.81, multiplied by v, volume, which is 4.6 centimeter cube. Be careful. This will be 4.6 divided by 100 cube. And the upthrust comes out as 0.0374 newtons. Now, let's write 0.37 plus drag is 0.32. So the weight comes out, sorry, this will be 0.037. 0.037. This comes out as 0.357, the addition itself, and up to two significant figures, this becomes 0.36 newtons for the weight. Product define momentum, that is a product of mass and velocity, simple and straightforward. A child stands on a scooter on horizontal ground. The combined mass of the child and the scooter is 16 kilograms. The child starts from rest and then pushes once on the ground and causes to accelerate. The push lasts for 1.1 seconds. The scooter after 0.6. Okay, fine. the average resultant force, so the force is equal to change in momentum divided by change in time, or the time required for this motion to happen. So this will be mass into change in velocity divided by time. The mass is given to us as 16 kilograms, so 16 multiplied by the change in velocity, which is 0.6. I believe it is starting from rest, so the original velocity would be 0, final is 0.6, so this will be 0.6 divided by time, which is 1.1. So when you solve all of this, your answer is going to be, or your answer is going to come out as 8.727. This is 8.727, which is going to become 8.7 newtons. Later, the child B travels down the slope at a constant angle to the horizontal as shown. At point B, her speed is, so at this point, her speed is 0.6 meters per second. She reaches point B with an acceleration of 0.85, and at this location, the time taken to go through A to B is 3.7. The acceleration in this direction is 0.85 meters per second square. I just like to write the data on the diagram. You could choose another method to do this, it's up to you. Calculate the distance x traveled. Okay, so there are going to be two ways to do that. There are many ways, but let's explore all of them. So you can directly use S equals to ut when it's about displacement in time, half at squared. So displacement is the x distance between A to B. Now ut would become as 0.6, the initial velocity at point A, time was 3.7 seconds, plus half into acceleration. The acceleration it experienced was 0.85. The time it experienced it for was 3.7 second whole square. Don't forget about the square. So the displacement from x A to B, if you solve this entirely, this is going to come out as 8.03825 meters, which is definitely going to become 8.0 meters up to two significant figures. Let's try another way. So what about finding the final velocity at location B? Could we have done that? Yes, we could have. So V equals to U plus AT. This will become 0.6 plus the acceleration 0.85 happening for 3.7 seconds gives us the final velocity as a 3.745. And then we could have used a V square equals to U square plus 2AS to do that. So this will be 3.745 whole square equals to 0.6 whole square plus 2 into 0.85 acceleration into S, which is of course the x between A to B. This also gives you S or x equals to 8.0385 meters, which is exactly 3825 meters, exactly by the other method. This is going to be rounded off to this value. Part B, he says, in part D, he says that it is at this location, and we remember that the velocity at this point was from the previous part, 3.7. Not that it's going to be required, but just writing this down for understanding. He says, now he applies the brakes to maintain the speed at a constant velocity. So it will be maintaining its speed, whatever it had from the previous journey. He says the work done between B to C by the brakes is 250 joules. The distance is also given to us. Determine the magnitude of force. Very easy. So work done is actually equal to force into distance. The amount of work done or energy removed from the system is 250 joules. The braking force did some work, and it was continuously doing the work for 18 meters. So the force that must have done this job should have been 13.88 newtons in magnitude, which is going to become 14 to two significant figures. On figure 2.3 sketch, because we're going to make an estimate, that's why it's a sketch, the variation of the kinetic energy, be careful, of the giant scooter with a distance traveled from A to C. You see, this is point A, this is point B, and this is point C. Now, the first question you should ask yourself is that, are we going to start the graph from the origin? Can we do that? Well, actually, we can't do that. Why? Because it already had a speed of 0.6 meters per second at this point, 3.7 meters per second at this point, and continued to maintain that speed until its end of journey, which is at point C. So if it is about kinetic energy, which is half mv squared, I should have a non-zero starting point because it's not zero when we started to read its motion. And now its velocity increased, so its kinetic energy increased, so it should be somewhere greater at this point at B. Now, since from B to C, he says that it is moving, let's say, at a constant speed or constant velocity, I will say that the kinetic energy is not going to change. The answer for half mv square will not change between B and C. That is why it should be a flat line. The problem is to figure out the first half. Should it be a straight line? Should it be a curved line like this one? Should it be a curved line like this one? This is the main problem. Now let's figure out what it's going to look like. So for that, we need to look at the equation, which is v square equals to u square plus 2as. If I choose half mv square, I can replace this whole expression in terms of v square because it is equal to v square. So 1 over 2 m into u square plus 2as. Is that a linear relationship, or is that a non-linear relationship? You see, this is equal to kinetic energy today. Whatever u square, whatever initial velocity it had, which was 0.6, it would already be calculated at all points, even if I draw new coordinates by measuring the distance, by measuring new velocities, by measuring for the sake of example, new distances. The distance is actually controlling the kinetic energy. So as far as you start to move, the kinetic energy will also be increasing by that method, by the standard. The acceleration is constant. The value of u is constant throughout its motion. The only thing changing is s. Now, s has a power 1, and kinetic energy also has a power 1. So there is a relationship that is actually linear between them, which is why this should be a straight line from the starting point up to any non-zero location up to this point. This is what the graph is going to look like. I hope it makes sense. Question number 3, he says stress is given to you. The variation of metal via P. Okay, fine. E is, I think, the elastic limit. Yes. Elastic limit is that point up to which point, if you start removing the force again, even if there is a bit of deformation, even if it starts to sway away from Hooke's law, it will still come back to its original position. So that's that. Young modulus for P. What I would do is I would choose the last extreme point generally. I can choose this point. It's crossing exactly from the coordinate. Or I would choose this point. In the marking scheme is taken this point, but I would likely choose the point that is furthest away to consider a larger portion of the graph. So if you look closely at this point, and at this point, you would realize that this is actually 24. And this is actually 1%. So Young modulus is actually equal to stress over strain. Now, luckily, stress is already on the y-axis and strain is already on the x-axis, but in percentage, be careful. So it could be called as the gradient. It could be just simply putting in the values. So this would come out as 24 into 10 raised to power 7. Why 10 raised to power 7? Because it's on the graph. 1% strain at that coordinate, so this is 1 divided by 100, equals to 2.4 into 10 raised to power 10 pascals. You could have done this at any other coordinate as well, but I prefer to choose the coordinates that are exactly passing from the point. It's easy to read them. So this will be 2.4 into 10 raised to power 10 pascals. On the line 3.1, draw across to show the limit of proportionality and label this as point Q. Now we know this from our experience that wherever the graph starts to curve is where it starts to leave Hooke's law. You see, wherever the line is extremely straight, this is the region or this is the space where it follows Hooke's law, right? It follows Hooke's law. And the moment it starts deviating, because Hooke's law is a proportionality of force and extension, the moment it deviates away from that path is the point where we find the limit of proportionality, because in this region, it is definitely following Hooke's law, which is being proportional, being a straight line mathematically. The moment it starts deviating away from it is the point where it starts disobeying Hooke's law. So this will be the coordinate which is going to be pointed as Q. Okay, part B, state the condition necessary for equilibrium. Again, we've done this in P1 MCQ as well. The resultant should be 0 and the resultant torque should be 0. Now this question is from Moments. A very simple question, straightforward. He says that it's a horizontal in equilibrium and uniform rod, which means that the center of mass will be exactly at the center. somewhere along this line, which will of course be divided by 0.65 divided by 2. And there will be a tension component in the wire. So he says that the wire is connected in the midpoint. He mentions it himself. So we can clearly calculate the distance from this point to this point for the sake of moment. 50 degrees horizontal, the shelf is attached. Okay, wall A, point A, the length of shelf is this much. The weight of the shelf is 33 newtons, which means that the weight of the shelf is 33 newtons. It's going to come here. The weight of the cup is 1.5 newtons, which is going to come here. So 1.5 newtons. He says that taking moments about A, which means consider this to be the pivot of the system, determine the tension in the wire. So for moments, this is the component of tension that is responsible for the anti-clockwise moment, and the red components are the clockwise. We are going to try to rotate the shelf in this direction. Only the tension component is going to try to rotate it in this direction. So this one is actually T sine of 50. And this component would be actually T cos of 50. We're not really interested in T cos of 50. We're interested in T sine of 50. So let's make the equation for clockwise and anti-clockwise. So let's take the anti-clockwise moment first, which will be T sine of 50, which is our force, multiplied by the distance from the pivot, which is definitely going to be half of 0.65. So I'm taking the full value over here, which is 0.65 divided by 2. Equals to the clockwise moment, which are going to be because of the shelf weight and the weight of the cup. So the shelf again is half distance from the pivot, which is 33, which is the force, multiplied by distance perpendicular, which is 0.65 divided by 2. Plus this is being helped by another moment provided by the cup. So the force or the weight of the cup is 1.5. The distance of the cup from the pivot. Now this is interesting. You have to take it from the pivot point A up to this point. 0.12 is not its distance. We take the distances from the pivots. So this will be 0.65 minus 0.12, which is definitely going to be 0.53. So when you calculate all of this properly, the value of T is going to come out as 46.2716 newtons. Again, I take full values, that's why. So this is going to be 46 newtons. So the tension in this rope is actually 46 newtons, irrespective of the components. The stress in the wire is this much. Determine the radius. Now, the formula for stress is force over area. Now, we know for a fact that the tension is the force in the wire. So stress is given as 1.5 into 10 raised to the power 7. The force is 46 newtons found in the previous part, and for the radius, it should be pi r square. So we are interested to find the radius. Please be careful that you have to take an under root at the end to find the radius. So the radius is going to come out as 9.87 into 10 raised to the power minus 4 meters. I've taken full value, so this is going to come out as 9.9 into 10 raised to the power minus 4 meters. More items are added to the shaft, doubling the stress in the wire. The wire is made of metal from P. So if we go back to P, it is the same material as shown in this graph. It's wire of metal P. So use figure 3.1. Now be careful, we have to go there. And state and explain whether the wire will behave plastically or elastically as the stress doubles. Now, right now, the stress is 1.5. If it is doubled, it becomes 3 into 10 raised to the power 7 pascals. Now, let's go back to the graph and see if it is a straight line. So, from the previous answer, let's remove that. So, at 3, we have 1, 2, 3. So, this is our 3 into 10 raised to the power 7. And as we can see that it is in the straight line region, it will still obey Hooke's law. It will still be in elastic region. So, it will behave elastically. That is what we've written down. Elastic limit has not been reached, hence it will behave elastically. Simple and straightforward answer. Question number 4. With reference to the direction of transfer of energy, compare the energy of oscillator. Now this is again a repeated question from IGCSE O levels. In longitudinal wave, we know that the particles are moving in the direction of or parallel to the direction of the transfer of energy. And in transverse wave, we know that the particles are moving perpendicular, so to the direction of propagation of energy. Very straightforward, very simple definition. A pipe shows, and now sometimes in these stationary wave questions, he will not show you this diagram. But luckily for us, in this one, it has. And you will always find that the open end will always have an antinode and the closed end will have a node in it. And that is one of the rules you can say for them. So he says, draw the letter A for the antinode. So you'll write down simply A here. Determine the frequency. Very, very simple question. See, this length that represents between a node and an antinode is actually quarter of a wavelength. If I had to draw this completely, this is how it would go. 4 times this length. That is why we're saying that this is quarter. If I want to find the full wavelength, if this is equal to 4.5, I simply have to multiply this number with 4 to get the full wavelength, because this is only representing a quarter wavelength. So V equals to F lambda. V is 340. Frequency is what I need to find out. And lambda is going to be 4.5 into 10 raised to power minus 2 multiplied by 4. The frequency comes out for this question as 118.88 hertz and so on. So up to 2 significant figures, this will be 1900 hertz. The piston is moved to the left. Now, if you move the piston to the left, you'll have more space, more and more space for this wavelength to capture or to exist in. So he says, if we do that, what's going to happen? So changed. Now, loudspeaker frequency is now changed. So the stationary formed with the same number of antinodes. What is he saying in this statement? He wants you to know that whatever the shape of the wave looks like right now, he wants to maintain that shape because only one antinode is there. He wants to make sure that only one antinode stays there. Because if you look at next cases, the next case would look something like this in this column. This will be antinode, this will be antinode. There will be 2 antinodes in the next harmonic. He does not want to do that. He wants to make sure that if we move the piston back, this is the shape of the wave that remains. Now, if that happens, the wavelength is going to increase. If the wavelength is increasing, what's going to happen to the frequency? You see, V is equal to F lambda. V is constant. The speed of sound is 340 given by the question by the examiner. So if you are increasing the wavelength because of the physical problem, because physical change, then the frequency produced by the sound by the speaker should also be decrease. So based on this idea, since the wavelength is going to increase in the column because we're physically changing it, the speed is constant. It has to be. So if you're increasing the wavelength, the frequency decreases, or you have to decrease the frequency produced by the speaker. Frequency must decrease by the speaker or produced by the source. Question 5. Electric potential, again taken from the past, taken directly from the syllabus. Energy transfer per unit charge from electrical to the forms or stores. Stores would be a better word. Power supply, 3 resistors are there. So this is a heater. This is what we've done here. Show that the potential, now again, it's a show that part. Potential difference across 0.86 is 6 volts. Very simple, very straightforward. The current through this resistor is 7 amperes. So we can simply apply V equals to IR to do that. So V equals to IR, current is 7 amperes, the resistance is 0.86, the value actually comes out as 6.02 volts. But since we are taking 2 significant figures, this is 6.0 volts, which is of course what we have shown successfully. Now you will be using this value for the rest of the question. You don't have to take up to 2 decimal places. He says determine the current I. Now I'm surprised that this part actually requires more steps than usual. This is for 2 marks, whether this should have been for 3 marks. But again, what can we say? It's the examiner. So, determine the value of current I1. He wants you to find the value of I1. So, if 7 amperes entering is this junction, we can figure out how much current goes to I2, and then we can simply subtract it from 7 amperes to get it from I1. Now, before we do that, we understand that 6 volts were lost by this resistor or were consumed by this resistor. So, how much voltage out of 230 is actually reaching these combinations? They are connected in parallel, the voltage will be the same, but how much voltage do they actually get? You see, 230 minus 6 volts taken by this resistor, we are only receiving 224 volts at this junction. So the voltage between this junction or these 2 terminals is actually 224 volts. This is what we will use for all our calculations. Let's figure out I2 first. So this will be I2 equals to 224 divided by the resistance of this combination, which is 170. And definitely, this is going to come from V equals to IR. So V equals to IR was modified to look like this. The voltage access was 224. The resistance was 170 for that branch. So I2 comes out as 1.3 amperes. Now, if 7 ampere is entering this junction and 1.3 goes to this branch, 1.3 amperes, so how much will be left to go to this branch? It is simple subtraction by Kirchhoff's current law. So I main, or the main current, is actually equal to I1 plus I2. The main current from the battery is 7 ampere. I1 we don't know. I2 is 1.3. So I1 would be equal to 7 minus 1.3, which becomes 5.7 amperes. So this branch is getting 5.7 amperes through it. This is receiving 5.7 amperes. All right. Now, and again, be advised that since it is receiving 5.7, some of the voltage will be consumed by this resistor according to V equals to IR, and some of it will be consumed by the heater according to V equals to IR. We can find them individually, we can find them collectively, your choice. Let's see what the question says. Again, I was expecting this to calculate the potential difference across component X, which will be V equals to IR simply. The current it received was 5.7. The resistance of component X is not given. That's why that part is tricky. So resistance of X is not known. Let's write it another way. You see, if I find the voltage consumption by 2.4 ohms, I can simply subtract it from 224 to find the voltage, how much X will consume, or how much voltage X will consume. So let's try to do that instead over here. So this is, let's say, V equals IR. So the current it receives is 5.7. Resistance of it individually is 2.4. Let's see what that gives us. So the voltage consumption by this method, let's say, is 5.7 multiplied by 2.4. This is 13.68. So this consumes 13.68 volts. And out of 224, 13.68 should be used by, should be available for resistor X equals to 5.7 into R. Let's find out the R in this method. So 224 minus answer divided by 5.7. This comes out as 36. This comes out as 36.89, which becomes 37, I guess. So yes, it becomes 36.8. All right. So now we can find the potential difference, which is again going to be multiplied by 5.7 to find 210.32. Actually, what you could have done is, if you notice, then 224 minus 13.68 would also qualify as a potential difference available for this component. And I think we have done that, the resistance part, as an extra bit. So there are multiple ways to do this. No specific way out of that. There is completely fine. This is going to be 210. Or you could have done, let's say, 224 minus 5.7 multiplied by 2.4. This would be the voltage available for that component. Again, any logic that you think is necessary, you can do it by multiple ways. Power dissipated in component X, this will be, I'm going to show this by all three methods. You can choose any one of them because we know that power is equal to IV, it is equal to I square R, it is equal to V square over R. But be advised, we're going to use values of this resistor only. So the current taken by this component was 5.7. The voltage it consumed was 210. The current was 5.7 square. The resistance it had was 36.8. No square over here. And then we had the third option, which is voltage square, which is 210 square divided by 36.8. Now, luckily, if you try it with all the options, in IV you get 1197 watts. In I square R you get 1198 watts. In V square R you get 1195 watts because of the difference of decimal places. At the end of the day, this is going to come out as 1200 up to two significant figures. So not really an issue here. The purpose of the circuit is to provide power to component X. determine the efficiency. You see, the whole circuit was designed to power X. How much power is X receiving? Actually, it's 1200. How much power the circuit is actually developing? That is going to be actually 230 multiplied by the current it is supposed to provide. So the power supply's input, or you can say the useful output, is for the heater, which is 1200. But how much is the total input, which is definitely the supply, 230 multiplied by 7. So when you do that, and then simply multiply this with 100, this comes out as 74.53%, which becomes 75%. The resistor of resistance 170 ohm is removed, which means that this branch does not exist anymore. It is removed, leaving the circuit open and the load branch. There is no change in the resistance of component X. State whether the current, the power supply increases, decreases, or remains the same. The current will decrease because the whole combination is in parallel branch. You see, the 1.3 amperes that it generally demands will now no longer exist, eventually putting less load on the supply. So the supply has to provide less current as compared to before. That's why the current is simply going to decrease. Question number 6, he says, compare alpha and beta. Again, from memory, they both have positive charges. It's a positron. Alpha is much more massive than positron. Alpha has a mass of 4u. Positron has a mass of 9.11 into 10 raised to minus 31 kg. Not that you have to mention this. I'm just mentioning this over here as a fact. Magnitude of charge on alpha is double or twice than of positron. And thus what we know, that alpha is 4, 2 protons it has. And but the positron is only a single charge, which is 1.6 into 10 raised to minus 19. This is 2 multiplied by the elementary charge, which is 1.6 power minus 19 coulombs. Now he says that we have a nucleus P undergoes alpha decay to become Q, and then Q undergoes another decay to become R. And a table is shown over here. So P, to our example, is 216 with 84. I'm picking values over here and here. And decays to become Q, alpha decay. So this is going to be, undergoes alpha decay to form Q. So let's find Q. So Q plus alpha is 42. Q should be 212. And this should be 82. And then he says Q then undergoes decay to become R. So Q again undergoes decay to become R, and for R we have 212 and 83. I can observe that the proton number increases from 82 to 83, which means that this must have undergone beta negative decay. And if I was to draw Q, it should have been at 212 but 82. This is where Q should have existed. So it says mark Q. We've done that. State the names of the particles emitted by Q decays to form R. So when Q decays to become R, this is what he wants to know. It's going to be a beta negative and an electron antineutrino. Again, for beta negative, electron antineutrino is the second particle that gets emitted. For beta positive, we have neutrinos with them. Before the alpha decay, P is traveling at a constant velocity, which means in this direction. After the decay, Q has a velocity of this much, and the whole situation is explained to you. Now, we don't have the forward velocity of particle P. If we had that, we could have used the horizontal components to solve this momentum problem. But since we don't have them, we cannot use those as an equation. But what we do know is that P did not bring in any vertical momentum. It didn't have those velocities. But the particles A and Q do. One of them is actually having a component like this one and like this one. And Q has a component like this one and this one. We don't have enough information about the horizontal components because the speed of particle P is not mentioned, but we do have information about the vertical components for alpha and Q. This is what we're going to use. Now, since the vertical components brought by P were equal to 0, we can say that the vertical components of alpha and vertical component of Q, if I add both of these components together, this should produce an answer equal to 0. Which means that if I simply do Q plus alpha, this should be 0. Or, in truth, it is actually like this. Q plus negative alpha is equal to 0. Bringing it over here, this makes it Q equals to alpha. If you want to get really technical, in terms of the sign convention, then this can be improved even further. You see, the upwards direction are taken as positive in physics and the lower directions are negative. So alpha, the momentum of alpha plus negative q should be equal to 0, and then q brought to this side, this should be q alpha equals to the momentums of q along the vertical plane. This is the idea we're going to use to solve for the velocity, I think the angle theta of this question. So he says, use principal conservation of momentum to find theta. Not a problem. Let's find out the equations for them. So since we're using momentum, this will be mass into velocity. And since it's the vertical component, this is actually the sine theta of the situation. So this will be, since we're dealing with alpha, this will be 4 times u, the atomic mass unit. This will be 4 times u. And we understand that in the data booklet, u is 1.66 into 10 to the power minus 27 kgs. Mass into velocity of alpha particle, which is 150 power 5. So 150 into 10 to the power 5. And of course, with the component of sine theta, because we're considering the vertical components. The second one is particle q, which is 1.3 power 5. So this is the mass of q, and this is 1.3 into 10 to the power 5. And its angle is given to us as 68. So this will be sine of 68. Now, what should be the mass of q? Do we remember what is the mass of q? We'll have to go back to q, which is 212 atomic mass units. So this is 212 U. What you could have done is you could have added 1.66 into 10 to the power minus 27 in this equation, but it will be cancelled from both sides. So no need to make this equation any more complex than it already is. We need to find or solve for sine theta. Don't forget to take sine inverse at the end. Once you've done with multiplication and division, your theta calculated as will come out as 25.206, which will become 25. Again, this answer is when you take full values, but you don't really have to do that. So the last part, calculate the kinetic energy of alpha particle, very easy and straightforward. So half mv square, show the formula to the examiner that you know what you're doing with. 4 multiplied by 1.66. Now you need to put in the atomic mass unit, and the velocity was already given to you. So 150 into 10 to the power 5. Now, amazingly or fortunately, if you weren't able to solve this part, don't lose hope. The next part is not dependent on the previous part. So please read the whole paper carefully to maximize your chances of getting credit as much as you can. So this comes out as 7.47 into 10 raised to power minus 13 joules. This becomes 7.5 into 10 raised to power minus 13 joules. Two significant figures. I hope you've learned something. That is all.